Welcome back. In our last video, we solved an example showing how we could discuss the differential of a complex function. This time around, we want to show that there are complex functions to which their limits do not exist. And in these cases, you'd say that those complex functions will be discontinuous at those set points. For instance, in this question we are considering today, we have to show that the limit as z tends to 0 of z divided by the absolute value of z does not exist. Of course, the absolute value of z in this case refers to the modulus of the complex number z. Now, this means that this complex function z by absolute value of z will not be continuous at 0. Now, how exactly can we do this? The very first thing is, let us start from the known to unknown. First and foremost, we would rewrite, or we will define the complex function, or the complex number in this case, as x plus iy, correctly quoting the real part and the imaginary part as necessary. In this case, it then makes it easy for us to define what absolute value of z is, which is the modulus, as we said, as the square root of x squared plus y squared. Now we have both terms written freshly in terms of x and y. Now, it means that if we're evaluating the limit as z tends to 0 of z divided by the absolute value of z, this, of course, is the same thing as evaluating the limit as x tends to 0, and then, of course, as y tends to 0 of x plus iy divided by square root of x squared plus y squared. That's what it means. Now, remember, for the limit to exist, the limit has to be the same value across all the single axes or lines that we test with. If the limit is not the same across any of those axes or across any of those lines, then the limit does not exist. Plain and simple. So let us test what happens along the x-axis, which in this case is our real axis, right? So along the real axis, we will have that means that y will be equal to 0. There is no need for the differential here because we are not looking for the differential. So in this case, y is 0, so that means the limit as z tends to 0 of z divided by absolute value of z will then reduce to being the limit as x tends to 0 of x divided by the square root of x squared, because y has become 0. Now, this is very, very interesting because you realize that the square root of a value is always going to give us a positive and a negative result. So this would mean that we would have the limit as x tends to 0 of x divided by plus or minus x, right? Because the square root of x squared will give us plus or minus x. Now, this is very, 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 very interesting. Now, being able to write this concept in this form adds a lot of complexity to this question, because it means that if, of course, we divide, we would have that the limit as x tends to 0, the function will then reduce to plus or minus 1, which already tells us that if we evaluate the limit, the result will just be plus or minus 1. So we already have ourselves two possible values for the limit. We already have ourselves two possible values for the limit. Now, that is already a problem because, remember, the limit of a function must be unique, and in this case, we already have two values. So that's already a problem. Now, if you still want to struggle and say, okay, maybe something interesting might still happen, let us evaluate along the imaginary axis, which is unnecessary, but just to give ourselves confirmation beyond every possible doubt, along the imaginary axis, x would be 0, correct? So in this case, we'd have that the limit as z tends to 0 of z divided by absolute value of z would be the limit this time around as y tends to 0 of iy, right? Because the x will vanish, divided by the square root of y squared, which in turn would mean that we would have the limit as y tends to 0 of iy divided by the plus or minus y value, which would mean that we would have the limit as y tends to 0 of plus or minus I, which should of course give us plus or minus I. So this time around, we have 4 different values for the limit. We have plus or minus 1 on the real axis and then plus or minus I on the imaginary axis. It's obviously going to remain this crazy even when we evaluate along the straight line, which in this case there is no reason to do that, because along the first axis, which is the real axis, we have already found ourselves 2 possible limits, and that already contradicts the fact that the limit of a function is unique. So since we are unable to find the limit value that is unique across all axes, if you are wondering what we mean by that, you can take a look at our previous video where, from the example we solved for the differential, you will see that the limit we obtained was unique across all the axes and lines we took. So that should also apply here. Since we cannot have the limit being the same across all axes, it means that the limit of the function does not exist. So therefore, we can generalize that the limit as z tends to 0 of z divided by absolute value of z does not exist. So this gives us an example of a complex function that is discontinuous at some particular point, right? And this is very, very, very interesting to keep in mind. Now, of course, does it mean that it's only discontinuous at 0? Maybe, maybe not. That leaves a lot for you to adventure into as far as this question is concerned. However, remember that a function will become discontinuous if it is discontinuous already at a point. Now, there are different kinds of discontinuities, as we will see later on within this playlist. As we proceed, you would notice different kinds of discontinuities: essential discontinuities, isolated discontinuities, removable discontinuities, as the case is, right? However, a function that is not continuous everywhere is a function that is discontinuous at least one point, and we have given ourselves an example of this. Now that we have solved a question on this concept, we will then take the next few videos to evaluate some pressing questions as far as how to simplify complex numbers in different forms. Now, complex numbers come in different varieties. It's not always going to be as simple as x plus iy. It could be in power forms, it could be in trigonometric forms, or in the arc-trig forms, or it could even be in a different form entirely. In order to deal with these possibilities, we would have no choice but to consider ways in which we can make these substitutions or simplifications as necessary. So our next few videos will consider this in detail. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.